Okay, here in this lesson we are going to discuss about the rate of a reaction. So this lesson based on the very simple knowledge with respect to the rate of reaction and chemical reaction. So here, when consider about rate of reaction, we can measure the rate of reaction in different ways. So when consider about rate of reaction, it can be measured as amount of reactant consumed within given time, or second one, amount of product formed within given time, third one, time required to consume for given amount of reactant, or time required to obtain given amount of product. So this is the four method, and these four method we can use to measure the rate of a reaction. So for example, now think about in this school or in your class, so I have given you now think about 100 mangoes. So I ask you to eat these mangoes within 25 seconds or within 30 seconds. Then we can measure the rate, or in other words we can say, so I will give you time for 10 minutes and eat mango as you can. So likewise, using simple example, you can understand these four: amount of reactant consumed within given time, or amount of product formed within given time, or time required to consume for given amount of reactant, or time required to obtain given amount of product. These are the four methods. But when considered chemical reaction, it is very difficult to measure using this method. But the best thing is to understand the method or study the rate of reaction is concentration changes of product or reactant. It is very helpful for the studies. Okay, now when consider about this one, it is very helpful to study about changes, concentration changes of reactant or product. Now let's consider about chemical reaction, and then you can easily understand what I mean here. Okay, let's consider about this chemical reaction. Now think about this one, 2a plus 3b convert into 5x. So when consider about this reaction, a and b are reactant and x is a product. So in this reaction, so we can get the concentration or rate of reaction idea for this one. So for rate of reaction, this one we have to get consume amount of A, or now think about A is a reactant, therefore we can consider about consume amount of A divided by the time, or within unit time, and you have to divide by the stoichiometric ratio, and this one equal to consume amount of B divided by unit time with respect to the stoichiometric coefficient, and this one equal to the product obtained amount. Okay, obtain amount of x divided by time into stoichiometric coefficient. And here it is a very special thing I want to explain here. So here consume amount means it is a consume of reactant, therefore for this one you have to use negative sign, and here also you have to use negative sign, and here positive sign. This is very simple one. Negative means consume, positive meaning just obtain the product. So this one also, so we can use this one as now consume amount of A, or we can consider as concentration of A. So concentration of A, normally we write with this notation with the bracket, and then time, normally we call the concentration changes related to this one as delta A equal, and time difference delta T, and stoichiometric ratio 1/2, and here also delta B concentration divided by delta T time difference into 1/3, and here also delta X concentration divided by delta T into 1/5, and when consider about the stoichiometric coefficient in this relationship, but this is meaning of this one, consume, and here also consume, and here it should be positive. So this is the relationship for the consume and the obtain or rate of reaction. So for this one normally we can write this is equal to the rate of reaction, rate of reaction is very easy to understand. So when consider about this one, this is the point, which is the relationship we can obtain with respect to any different equation. So let's consider about another equation. So when consider about this one, let's consider about this reaction, and 3x plus y convert into 2z. So according to that relationship we can write rate of reaction equal delta x over delta t, it should be negative, into stoichiometric ratio, and equal negative sign delta y divided by delta t stoichiometric ratio 1, no need to mention it here, and here positive delta z concentration divided by delta t into stoichiometric ratio 2. So this is the relationship for any type of reaction. We can write rate of reaction using this relationship. Okay, then we'll move on to the next slide, and it is about the rate of reaction. Okay, now consider about this one. So this is the note in your tube, and you can study about this note, and just take your print out for this one. Okay, so when consider about chemical kinetics is the study of reaction rate, that is how fast is given reaction does proceed. That is the meaning, as I said before also. So measure of rate of reaction, it is the measure of the change of the concentration of reactant or product as a function of time. So this one also I just explain about this one very simply. Okay, then reaction rate provide information regarding how fast chemical process occurs, as well as the mechanism by which a reaction occurs at a molecular level. So now there is different type of requirement that should fulfill for the chemical reaction, requirement that should fulfill for a chemical reaction. Then the first one, the reactant must collide. Collide means it should have collide, if not reaction will not start. Then the collision between molecules in chemical reaction provide the kinetic energy needed to break the necessary bond, so that new bonds can be formed, or collision should be moved to the right direction, or normally we call right direction or right orientation. Right direction or orientation. Direction or orientation. Okay. Right direction or right orientation. They must have enough activation energy in molecules. So sometimes we can merge this 2 and 3. So first one we call the reaction must collide, and second one we call they should have actually gathered with the activation energy, and also the collision should be in the right direction. Also we can merge 1 and 2, and 3 we can left as a 1. So we can summarize these 3 factors as a 1. So example I will say, so when consider about cricket match, think about cricket match. So now think about the world famous cricketer Virat Kohli. Now think about he want to hit a 6. Hit a 6 means the ball should collide in the bat, if not it's a problem. So, and also the second one, the ball should collide in the right direction. If there is a collide in the edge, then there is no 6. So, there is no reaction, same as. So, the first requirement should collide in the right orientation. Okay, and second, so first one and second one merge, and then third one we can explain, and that collision should have gathered with the activation energy. Activation energy means if he has not energy, then he can't pass the ball into the boundary line. That's all. Okay, so likewise, so we can summarize these two properties as a one. So one requirement should collide in right orientation, very simply, right orientation or right direction. This is the first one, and third one or second one we can consider as the, at least they should have gathered with activation energy. I will explain about this activation energy, and just this is the factors. So the requirement to start a chemical reaction, we should have gathered with activation energy and should collide in the right direction or right orientation. So this is the simple thing you want to understand here. Then we'll move on to the next one. Now think about, when consider about the chemical reaction, there is a special word we have to study about this one. Normally we call activation complex. So activated complex and activation energy, these two factors. So first I will explain about activation energy, then I will explain about activated complex. So activation energy, consider as it is defined as the least possible amount of energy which is required to start a chemical reaction, or the amount of energy available in a chemical system for reaction take place. That means, that's why I said, so if here that Virat Kohli want to hit a 6, then he should have some minimum energy. So that's energy we called activation energy. So that should complete the activation energy to start chemical reaction. And then this one called activated complex, and activated complex is an intermediate state that is formed during the conversion of reactant into product. So this is intermediate activated complex, and activated complex is the structure that results in the maximum energy point along the reaction path. The activation energy of a chemical reaction is the difference between energy of the activated complex, and then highlight this part, activated complex and energy of the reactor. So this is the part. So I will explain about the activation or activated complex also. Okay, so now we'll move on to next part. And then, so when consider about chemical reactions, there are different type of reactions. Normally we called, first type of reaction we called elementary reaction. Elementary reaction, or within bracket no molecule, called one-step reaction. One-step reaction or elementary reaction. So elementary reaction just form, and there are two types of elementary reaction. First type of elementary reaction we called endothermic reaction, and you have to make your note within the given space. Okay, endothermic, and second one we called exothermic reaction. So you know about this one, endothermic and exothermic reaction. So now I am going to explain about this one with respect to the activated complex. So when consider about the exothermic reaction, so when consider about this exothermic reaction, actually there exist now think about this graph, you have to draw it in your note. Okay, now think about this graph. So in exothermic reaction, energy in the reactant are less than energy in the product. So when consider energy in the reactant are higher than the energy in the reactant. So this is the reactant, and this is about product, reactant and product. So when consider about this reaction, what's happened here is during the reaction, just start from this point and then reactant convert into product through this type of process. So when consider about this one, this is the maximum point that has the highest energy. So this point there is an intermediate we call, that is the activated complex. Activated complex. So this is the point that has activated complex. In this point you can see here. So this is the maximum point. So in this type of reaction, so activated complex means, so I just explained previously also, the energy gap between reactant and intermediate. The energy gap between reactant and intermediate. So this one we consider as the activated energy, or normally we call activation energy EA, up to this point. Okay. So the energy difference between reactant and product, normally we know the related to this one and this point, this is related to delta H, this is delta H. So this is the energy level diagram with respect to exothermic reaction. Okay. So when consider about endothermic reaction, this is somewhat different. When consider about endothermic reaction, okay, when consider about endothermic reaction, the energy in the reactant are less than energy in product. So this is reactant, and this is product. Therefore the reaction start from this point, unlike we'll use red color, and reaction start from this point and like this, start like this. Then you can easily understand what about this one, and this is the point of activated complex, and here it is a point, this normally we call, this is activated complex for exothermic, endothermic. Activated complex, this is related to endothermic reaction. Okay. So here also we can get the definition, the energy difference between activated complex and reactant called as the activation energy. I will use another different color. Okay. So and this energy we called as the activation energy, and the reactant, the energy gap between product and reactant, and this gap we call delta H. So in the given space in your tube, you have to make this graph. Okay. So this graph, y-axis is energy. Okay. Y-axis related to energy, and this axis related to energy, and forward. So this axis normally we use time. Okay. No problem. And then make your note in the given space of your tube. So now I think now you have idea about what is the activated complex, and what is the endothermic reaction, what is the exothermic reaction, how it's joined with the activation energy. So activation energy, just keep in mind the definition. So definition shows that the energy gap between reactant and the activated complex, that is the important point. Okay. EA equal energy gap between reactant and activated complex. This is the definition. Just try to understand this simple thing. Okay, then now I am going to move on to the basic part of the chemical reaction, and then now think about this one. So these are the factors that affect on the rate of reaction rate or rate of reaction. So there are 1 2 3 4 5 6 7 factors. So first factor we called surface area. Now think about surface area, how it's affect on the chemical reaction. So now think about if you want to make a tea, then now think about if you add sugar in powder form or sugar in crystal form. So what is the shortest time to get the point with the powder form? That's how its effect on the chemical reaction surface area. And then second one, temperature. Third one, radiation like sunlight or something. And fourth one, concentration or pressure of reactant. And this one, presence of or absence of catalyst. We are going to discuss separately about these things. And then activation energy, as I said before, and agitation or style. So these are the factors you should know, the related to factors related to rate of reactions. Okay, so let's move on to the next slide. In this slide I am going to discuss how surface area affect, and I am going to discuss separately about factors. Okay, surface area. So surface area means it is exposed to matter of solid substance. Imagine that you have I have given examples, perfect cube of magnesium, or the surface area is the sum of the cube area or 6 sides of cube. The surface area of the cube can be increased by dividing into cube into smaller cubes. Surface area is maximized when the single large cubes are crushed to fine powder. The rate of reaction of solid substance, so this is like actually I just explained about sugar powder and sugar crystal. Likewise, sugar powder and sugar crystal have they have some surface area, but when considered powder they have more larger surface area than sugar crystal at the same amount. If you consider about 1 gram of sugar or 1 gram of powder sugar or 1 gram of crystalline sugar, then 1 gram of powder sugar has the highest surface area as a powder form. So rate of reaction of a solid substance is related to its surface area. When reaction between solid and aqueous, liquid or gaseous increase in the surface area of the solid phase, reactant increase the number of collisions per second, therefore increase the reaction rate. The reason for this one, actually this is in details, and here I have given in red color that summarize the number of collision per second between magnesium or hydrogen is higher, and the rate reaction is the faster when considered about magnesium and hydrogen reaction. Okay, so reason is the surface area effect on the reason is the number of collisions per second increase. That is the reason to increase the rate of reaction, because rate of reaction depend on two factors: should collide in right orientation or should activate with the gather with the minimum activation energy. So here the reason is it collide with each other within given time, and the increase in the collision. Okay, so then we will move on to the next factor. Okay, then next factor. So when consider about temperature, now we want to think about how temperature affect on the surface area, rate of reaction. Okay, now think about, with the exception of some precipitation reaction involving ionic compound and like temperature. Okay, so when consider about temperature increase, normally we call increase in the temperature by say 10 Celsius cause some of the intermediate speed molecules to move faster. The result is more molecules is sufficient kinetic energy to form activated complex. So reason is to increase the temperature is kinetic energy and the increase upon the collision. So this is the reason. I will explain how it's happened. Okay, when consider about temperature, now I will say I will take very simple example. Now think about you have this type of two beakers, Now think about same volume. This is about we have used magnesium. Think about here we use 1 gram of magnesium powder, and here also we have used 1 gram of magnesium powder, and now we are going to add HCl to this one, HCl, and here also we are going to add HCl. But here solution temperature, now think about this is 70, and here solution temperature may be 30 degrees and here 70 degrees. So now think about, I am going to add HCl in different temperature conditions. So the reaction that may undergo here is magnesium plus HCl is the product magnesium chloride plus hydrogen. So as a reaction rate we can obtain the volume of hydrogen within given time. So as an observation, then you can say the hydrogen volume, as observation we can say H2 volume at 70 degrees is greater than H2 volume at 30 degrees. So this is the observation. So simple example, now you can say at different temperature stage the rate of reaction will different, but with the increasing of the temperature the rate of reaction also increase. Now we will move on to the Boltzmann curve. I think you just remember what this one in gas phase reaction. Yeah. So when consider about Boltzmann reaction, and this is x and y and x is axis, and so this axis normally we consider as the kinetic energy. In your tube you have to draw this graph also, okay, and here number of molecules or molecule fraction, okay. So you just remember about that graph start from 0 and just like like this type of graph, not touch the axis, okay, sorry for that. And then when consider about another temperature, high temperature than this one, then the graph should be like this. So here now think about this is T1 and this is T2 temperature, then T2 greater than T1. At this point now think about the activation energy for the reaction is the completion point related to activation energy is this point, and this is the activation energy we want to gather, the minimum activation energy EA. So at the initial, so cross reaction, the molecules with respect to T1 temperature is like this. So after addition of the different temperature T2 greater than T1, then the number of molecules will increase like this, and then activation energy, just number of molecules gathered with activation energy increase. So this is the reason why temperature effect on the rate of reaction. So here the reason to increase the rate of reaction is molecules with molecules gathered with activation energy increase, and therefore rate of reaction increase. So this is the graphical representation or graphical explanation the effect of the temperature. I think this is very simple thing you can understand, okay. Then I am going to move on to the 1, 2, 3 next factor. sorry, this is some simple properties of effect of temperature, and rate of reaction increase with the temperature, and molecules that have enough kinetic energy increase with the temperature, and that affects on rate of reaction mainly. Collision rate also increase with the temperature, and that is effect on rate of reaction insignificantly, but there is some effect, very simple effect. If activation energy for a reaction is low, then rate of reaction is high. If activation energy for a reaction is high, then rate of reaction low. So that means activation energy low means high reaction rate. And the disadvantages for increasing rate of reaction by temperature, there are some disadvantages. So excess cost for heat generation. Now think about, if you want to high temperature condition, you have to use high cost for the electricity or gasoline or something. So and sometimes it may be explosive reaction or explosive. So those are the effect of the temperature on rate of reaction. Now we are going to move on to the catalyst part, and I think you know now what is a catalyst. A catalyst is a species that is speed of chemical reaction without being chemically changed upon completion of the reaction. There is no contribution in chemically. In other words, the mass of catalyst is the same before and after the reaction. Catalyst does not contribute to the reaction by stoichiometrically, and catalyst reduce the sorry, this is wrong. Okay, just cut it in your note, not catalyst reduce the activation energy. Then before 2019 it's just okay, but after 2019 new syllabus they just change this word. Okay, catalyst reduce the activation energy, and this is incorrect. Okay, and in your tute just make it okay incorrect one. Okay, just change it with the syllabus changes, that's a problem. Okay, so when consider about activation energy, and this is the catalyst. Catalyst does not change does not reduce the activation energy. Okay, so normally the what we call this catalyst shows an this is the point you want to understand. Okay, this is what happened. Okay, catalyst shows a different path with low activation energy. That is the point that we can use for the titration, sorry, contribution of catalyst on rate of reaction. So I will explain using energy graph. Think about this one. Sorry. Now think about this energy graph. Now if this is a very elementary reaction. Now this is, think about, this is reactant and this is the product. This is related to exothermic reaction. Okay, so this is the normal reaction with respect to the reaction, and this is reactant. Okay, and this is product. So what's happened is, after addition of catalyst to this reaction, it shows different path with low activation energy. Okay, different, and here this is the activation energy for the EA for initial reaction, and this one activation energy with low activation energy with low mechanism part. that's what's happened during the activation energy. Okay, or we can explain using the Boltzmann curve also. So what's happened is when you draw the Boltzmann curve for this one, sorry, okay, if you draw the Boltzmann curve for this one, it's maybe like this. So if we consider about the reaction and this one, this is the activation energy EA of initial reaction, and then this one is the activation energy with low activation energy path, low activation energy path, and this is the path with respect to the low activation energy path. So as a result of this addition of catalyst, must happen is the number of molecules. Now think about, these are the molecules at the initial that gathered with minimum activation energy, but after addition of catalyst there are no more molecules. Then the increase, or the reason for this rate of reaction is the number of molecules gathered with activation energy increase. So this is the reason after applying of catalyst for the reaction. Then now I am going to explain about some other different factors of catalyst. Sorry. Okay, so when consider about the catalyst, okay, this one. Okay, these are some examples used in the catalyst, common example for catalyst. So just read it. I just explained about this one also. Iron Fe used as the manufacturing in ammonia Haber process, platinum in the conversion of NO2, and also you just in organic chemistry I just explained about the for the conversion of carbon-carbon double bond into carbon-carbon single bond, we use platinum or nickel or palladium. These are some examples with respect to the catalyst, usage of catalyst. Okay, now let's okay, so these are some characteristics of catalyst. Okay, catalyst remain unchanged in mass and chemical composition in the reaction or activity of catalyst at the initial low at the end of the path. So there is no change in catalyst amount of catalyst, just there is no contribution stoichiometrically to the reaction. So this is some common characteristics for catalyst, and a small amount or quantity of catalyst is required. That's also another factor. And the catalyst does not change the equilibrium constant, but equilibrium approach earlier. At the equilibrium lesson I just explained about that, does not change the equilibrium constant. There is no change of no change of Kp and Kc, but equilibrium approach earlier within limited time. No change of this equilibrium constant, just keep it in mind. Okay, Then these are 3 factors, and then fifth one, specificity of catalyst. Then the catalyst is specific in nature. It means by the change of catalyst, the nature of the product change or a specific catalyst for a specific reaction. That means when consider about the Haber process, N2 plus H2 convert into ammonia. For this process, iron is the only catalyst we can use. We can't use nickel or any type for this one. So when consider about the alkene process, C triple bond or C double bond, the only catalyst we can use nickel or platinum or palladium. That means normally we call this is the specificity of the catalyst. Very simple. And then fifth one, the catalyst cannot make impossible reaction to occur and does not initiate reaction. Just keep in mind, okay. So it can't start a reaction, just catalyst just only given a very helpful path to start undergo reaction, okay. Then let's consider about the next one. And then there are some point we call catalyst poisons and catalytic promoters. Two type of, there are certain substances which decrease or destroy the activity of catalyst. Such substances are known as catalyst poisons. So it can decrease the activity, arsenic and this one. And also I just explained about another one, catalytic poison. I will go to next new slide, okay. And catalytic promoter means there are certain substances which increase the activity of catalyst. There are some examples given. I will give another 2 examples, okay. So when consider about catalytic poison, so could you remember this reaction, C triple bond C, if you want to convert into C double bond. So if you use hydrogen with platinum palladium or nickel, then this will end up reaction with alkane. So for this process I just explained that you have to use quinoline with barium sulfate, and here this one is catalytic poison and this quinoline process. And catalytic promoter means and nitrogen, hydrogen in the Haber process just from ammonia. For this iron used as the catalyst. So but as a catalytic promoter we can use Al2O3. This is catalytic promoter, okay. Just make your note as a additional point, okay. So there are another different type of point we want to discuss, and here let's go to next one. No, not this one. We'll go to previous one. Sorry, we'll go to new slide. Okay, and when consider about catalyst, there are some another different point also. So there are different type of catalyst. Normally we called homogeneous catalyst and heterogeneous catalyst. Homogeneous catalyst means reactant, product and all are in similar physical state, and the heterogeneous means the product may be different to catalyst in the physical state, okay. So when consider about the production of normally we call the homogeneous catalyst. Homogeneous catalyst. Homogeneous catalyst means all the product and reactant are in the same physical state. When consider about the H2SO4 production, in that process we normally use sulfur dioxide plus oxygen convert into SO3, and this reaction is used in these all are gaseous phase. In this process we use NO as the catalyst. NO as the catalyst for this reaction, NO gas catalyst. That means, and these all are in gaseous phase, and this one also in gaseous phase. Therefore this is the reaction, and this is homogeneous catalyst. all the factors are in all the product and reactant in gaseous phase. This is homogeneous catalytic active. Okay, then this is related to gaseous phase. Okay, then let's consider what another type of homogeneous catalyst with respect to liquid phase. Yeah, homogeneous catalyst in liquid phase. Okay, liquid phase. And here also, and when consider about the decomposition of H2O2. H2O2 normally we know the reaction H2O plus O2 for this reaction, and this whole line liquid phase. Okay, and here H2O2, and this is actually this product H2O2 at liquid medium, and this one also liquid, but at this point normally we use I minus or HI. Now think about HI, aqueous medium used as the catalyst. So here this is liquid medium and this one also liquid, therefore this is the homogeneous catalytic active at the liquid phase. And then consider about the heterogeneous catalytic active, and also we discuss about this one. Heterogeneous. Heterogeneous means, now when consider about nitrogen plus hydrogen, Haber process, ammonia production. This is gaseous and this is gaseous, this one also gaseous, but we use iron powder as the catalyst. And when consider about sulfur dioxide plus oxygen into SO3, these all are gases, but we use V2O5 solid as the catalyst. So these are example for heterogeneous catalyst. Within given the tube, you can make Q0 in a given spaces. Okay, so then we will move on to the next one. Then we just discuss about the different factors and with respect to the rate of reaction, and we just discuss about how it's affect the surface area, temperature, and presence of absence of catalyst. We just discuss about these factors, but when consider about radiation, it is very similar one. Now you just remember the this reaction CH4 plus Cl2 in the presence of HNO, and this convert into CH3Cl, and this is example for radiation of sunlight. So after addition of sunlight radiation, what's happened is the rate of reaction increase due to the open new site for the reaction. And when consider about concentration effect, and if we use high concentration and low concentration, we will discuss this one later. And agitation of sty, this is normally physical thing. Now think about if you use agitator sty, the rate of reaction increase as a result of collision increase. Collision increase. Okay, then activation energy, I just explained about this one also. Activation energy, if you fast the activation energy, then number of molecules gathered with actuation energy will increase, and then as a result of this one they increase the reaction rate of reaction. And then finally we will discuss about how concentration effect on the rate of reaction. Concentration effect. Okay, when consider about concentration, now think about, I'll suggest simple examples same as previous one. Now think about this type of 2 beakers here, and now think about 1 gram of magnesium med, 1 gram of magnesium med, and for this one we add 0.1 HCl, and for this one I think about we just add 1 mole per cubic decimeter HCl, 1 HCl. Then after addition of this one, as I said before, the reaction between HCl and this one is magnesium chloride plus hydrogen. So you can observation the nothing about hydrogen, the H2 volume in 1 mole per cubic decimeter HCl will greater than HCl is greater than that of 0.1 HCl. So this is how the concentration effect. And when consider the concentration, the main reason to increase the rate of reaction, the collision will increase. This is the reason. Collision will increase, as a result of that the rate of reaction will increase. So these are the factors that affect on the rate of reaction. In your resource book you can see a different type of chemical experiment also using they explain about these factors. Okay, so this is the same one, sometimes they may give some different reactions. Okay, so sorry, then I am going to explain about a new part. This is sorry, okay, so this is reaction rate. The rate of reaction is a measure of the change in the concentration of the product over time. Then rate can be measured at the beginning of the reaction, which is called initial rate. At any point the time of reaction and called that instantaneous react rate, and over at an interval which is average. These are only different word. Okay, and in the initial rate, the change of concentration of a reactant or product as a function of the time measured within given minute. I have explained at the initial this one. Determination of the dependence of initial rate of the concentration reactant or source derived rate of rate law. This is the point we want to use, rate law. I am going to explain about rate law, how its effect on the calculation. Okay, just read and complete your note. Okay, now actually nothing to complete, only thing you have to read it. Okay, now think about chemical reaction. I will go to new page. Okay, when consider about reaction, the reaction mechanism describes the sequence of elementary reaction. I just explained about elementary reaction, and that's mean one step reaction, and reaction intermediate I just explained, but here it is related to actuation energy. And when consider about chemical reaction, there are two types of chemical reactions. Okay, we called elementary reaction. First type of reaction we call elementary. Second type, this one elementary or one step. I think I'm not sure these are in tune, but you have to make your note. Okay, and second one we called multi-step. Multi-step reaction. So when consider about elementary reaction, the major difference between elementary and the multi-step reaction I will show using graph. Okay, So when consider about elementary reaction, it may be like this, and multi-step reaction like this. So when considered elementary reaction, and this is reactant and this is product, this may be different. So this is the elementary reaction through one intermediate, and here reactant and here product, and this is the intermediate, and elementary reaction only through one intermediate. So when consider about the multi-step reaction, they may have different type of like this 1, 2 or 3 type of they may contain 2 or 3 steps. So here this is reactant and this is product. When consider about single step reaction, activation energy for this one we call, this is the activation energy, reaction reactant and intermediate EA. When consider about this one, this is the first intermediate and this is the second intermediate, this is the third intermediate, and first, second, third intermediate, and here second intermediate, and here first intermediate, first, second and third intermediate. So here activation energy, now think about this is related to E1 and E2 and here E3. So this is the here. So E1, E2 and E3 are the intermediate activation energy. Now think about if there exists a difference between this E1, E2 and E3. Now think about, just think, okay. So this is elementary reaction and this is multi-step. So this is the main difference between elementary and multi-step reaction. So when consider about this activation energy, you can say, and here E3 is the lowest one, and then normally we call the lowest one is the lowest activation energy is the speediest one. Low activation energy means high rate, just keep it in mind, okay. So when consider about the consider about the rate mechanism described there. Reaction intermediates are formed one step and then consumed in the later step of the reaction. I just explained about this one using graph, and then slowest step in the mechanism is called the rate determining step. This is very important, okay. Slowest step is the rate determining step. Slowest step means the high activation point, high activation energy, okay. This is very simple example. Now I will say you, now think about you want to go to Colombo through highway. You start from Galle. Now think about your vehicle speed is 100. Now when you go to the Colombo side, there is a vehicle in the front, it is going with the speed with 60 kilometers per hour. Then your speed 100 and the next vehicle is 60. So what's happened? Your rate, you have to slow down your vehicle. The reason is the slowest one decide your speed. That is the point. The slowest step decide the rate determining step. The slowest step in the mechanism is called as the rate determining step. So that is very simple. Try to understand using that example. Now I am going to explain about new one, rate law, okay, rate law. And now think about there's a case, the rate constant x, y, and I think there is a space, you have to use that space, okay. I will give. Now think about chemical reaction. Now think about this chemical reaction, A plus BB convert into CC. So for this type of reaction, rate reaction means normally we call rate equal, this K is the rate constant, and normally we call concentration of A into power M and B into power N. This is the rate reaction. Here K called as the rate constant and M called as the order of the reaction with respect to concentration of A, and N order of the reaction with respect to B. So this is the definition in your note. Just make it and just highlight there is no relationship between M and stoichiometric ratio, no relationship, and here also no relationship in this one. So this is totally different. Just try to keep it in mind. This is the important point of the rate reaction. Okay, so now this is the point, and then I will go to the slide using of this one, and then in this slide the given space you can write here K is the rate constant, X and Y are the rate order, sorry not X and Y, actually just make it, and here just make it as in my, this is M and this is N reactant, and the order of rates are M and N are not related to the reaction coefficient. That's why I explained the value must be experimentally determined from the set of kinetic, for example the rate law for action. Okay, now I just explained about two types of reaction, one step and multi-step reaction. Now think about one step or elementary reaction. Now think about this reaction. This is 2A plus 3Z convert into X. There is no problem for this side, the rate flow with the reactant. Okay, so now if this is elementary reaction, if this is elementary reaction, this should be given. Okay, in the exam also there should be given, if not you don't know. If this is elementary reaction, then we can write rate as the concentration of A times stoichiometric ratio and concentration of C times stoichiometric ratio and rate constant. This is only applicable for if this is only elementary reaction, should be given. This is only for elementary reaction. Just try to keep in mind this is valid only for elementary reaction. Okay. Valid only elementary or one step reaction with respect to stoichiometric coefficient. If they have not given the as the stoichiometric elementary reaction, then you can't use this. Okay, then I am going to move on to the chemical calculation part with respect to this one. Then we will see how we can find experimentally. Okay, now think about this is think about this is set of experimental data with respect to this reaction, and here sorry, it should not R, actually should be the arrow mark, not R. Okay, so in this reaction there are some stoichiometric ratio, but you can't use for the, and for this one consider the following kinetic data for the reaction, and you have to find the rate of reaction for this one. So first thing you want to do is you have to write the rate reaction. Okay, rate reaction, and then you have to substitute this data to find the order. Okay, now think about we don't know the order. Now think about, sorry, now think about you can write rate as R equal K times here S2O3 2 minus into just get X and I minus into Y. You can't use X and Y as the stoichiometric coefficient, you have to find it. Okay, so I am going to substitute this reaction for 1. You don't know the value of X, K, actually it is not needed. So for first this one, rate equal 1.5 into 10 to the power minus 5. You have to use unit also, but here I have no enough space. Okay, and K times thiosulfate concentration 0.038 into X, and I minus 0.06 into Y, and for second one 2.8 into 10 to the power minus 5, and K times thiosulfate concentration 0.076 into X and 0.06 into Y, and third one 2.9 into 10 to the power minus 5 equal K times 0.038 times X and 0.12 times Y. So now just name these reactions as 1, 2, 3. Then I'm going to use it. I'm going to clean this part. Okay. Actually, it's very difficult for me. Okay, actually in this part you have to study only, you should have knowledge about the indices. Okay, so when consider this one as 1, this is as 2, this one as 3, then you can divide 1 by 2, then what's happen? 1.5 into 10 to the power minus 5 divided by 2.8 into 10 to the power minus 5 equal 0.0, K will cancel out, into X over 0.076 into Y into then 0. Here 0.06 and 0.06 cancel out, then here 0.03 and Y cancel out, no problem for this side, and then here the answer will be 1/2 into X, and here also approximately equal, you can use that type of one. For 15 or 28 means 1/2, then value of X equal 1, and this is the order with respect to thiosulfate. And then you have to divide by 2 by 3, then 2.8, 2.9, and then you have to consider about 2 answer. Not sure, I think it should be 10 to the power minus 5, no, sorry, we'll see. Okay, yeah, 10 to the power minus 5, sorry. Sorry, it should be 10 to the power minus 5. Okay, when consider about 2 by 3, then you can get the answer 2 over 3, then here final answer will be 1 in the left side, other side, and 0.76. No, let's consider about 1 over 3, because if we get 1 over 3, then 0.03838 cancel out, then no problem with X. Then consider about this one. Yeah, I think this is, you just find X and then consider about 1 over 3, then 1.5 over 2.9, then approximately equal to half in other side, also half into Y, then Y also 1. So when consider about reaction now, X and Y 1, X equal 1, Y equal 1, therefore we can write rate equal K times S2O3 and I minus. So this is the order. When consider about overall order, 1 plus 1 2. So if you want to find the value of K and substitute data with respect to any experiment, and then you can find the K. So for now consider about first experiment. You know the value of R, you know the value of thiosulfate, you know the value of 5 minus, then you can find K. This is very simple. And now I am going to move on. If you have any question, ask me, okay, in group also. And this is now another one, and here the experiment related to this one, and here also not R, it is the reaction point, and 3 product. For this one we can write the rate reaction R equal H2O2 concentration times X, I minus time Y, H plus time Z, and here you should have K as the rate constant, and then you have to substitute value, then you have to put the X, Y and Z. So with this one and along with this one I will send the tutorial also. You have to complete it and send me the answers. So I will give another more example. So here if you you can clearly check. So if you divide 1 and 2, then this will cancel out, this will cancel out, only remain this one. Then you can find from 1 and 2 you can find X. Here half and here also half, final answer 1. And if you divide 2 and 3, this will cancel out. It is difficult, you have to find, okay. Then try to find the answer for this one also if you have a question, okay. So this is the end of the calculation part. There is another part I will edit later, okay. This is the second part, okay. So this is the end of the first calculation part, and with this